So I have a pleasure of introducing Karen Chin Snyder, Senior Staff Physicist and Director of Treatment Planning at Henry Ford Cancer Institute. She'll discuss her study, a feasibility study of the magnetic resonance imaging guided adaptive radiation therapy, QA on the Viewray MRidian and Elekta Unity using the LUCY MR Phantom and the adaptive inserts. My name is Umar Baharom, and I'm the product manager and OEM strategic accounts at Standard Imaging. And then I'll follow up Karen. We'll have a quick look on the LUCY ThorX Phantom and the new adaptive inserts sets for prostate and spine cases. Whether you're advancing SRS, SBRT, MRgRT, or adaptive workflows, we hope that this webinar will show you how the LUCY MR and LUCY ThorX Phantoms can be helpful tools for commissioning and periodic QA. So now I'll pass it over to Karen to start her presentation.
Hello, good morning. Thank you, Umar, so much for the introduction. As Umar said, my name is Karen Chin Snyder. I'm a physicist at Henry Ford Health Systems in Detroit, Michigan. And I'm excited today to talk about our study on the intracranial MR-guided adaptive radiotherapy. Oops. So today the plan is to talk a little bit about some of the clinical motivation for adaptive intracranial radiotherapy, talk about the design and implementation of the MRCT visible phantom insert, review some of our results, and then discuss some clinical implications. So as many of us know, stereotactic radiosurgery and fractionated stereotactic radiotherapy is an effective treatment for brain metastasis. Some of the challenges include treating post-operative cavities, where the time from surgery to treatment is often important, and dynamic changes in the target volume may occur due to swelling and/or healing, as well as different pathologies. Some have more cystic lesions leading to variable target volumes. All these different soft tissue changes are difficult to see on cone beam CT or other X-ray based localizations on C-arm based LINACs. So this is an example paper from Japan that shows that these soft tissue changes, along with the sharp dose gradients in radiosurgery, can lead to lower doses to the target, as well as additional dose to the normal brain tissue. So a nice option that it has become very popular over this past several years is the hybrid MR-LINAC, which combines a daily MR imaging with the RT linear accelerator. It enables for daily adaptive planning, whether it be for visualized target volume changes or to adapt for setup variability due to the limited couch corrections available in these two systems. The two commercial systems used currently in the United States are the Viewray MRidian, shown on the top with a 6 MV flattening filter free beam. Oops, I have this one, 0.35 Tesla split magnet, and the Elekta Unity, shown on the bottom, which is a 7 MV flattening filter free beam, 1.5 Tesla with a closed magnet. And for both of these systems, the magnetic field is perpendicular to the linear accelerator. So in our study in collaboration with Standard Imaging, the goal was to develop and test an MRCT visible adaptive phantom insert, demonstrate adaptive workflows on the two MRL platforms. And all this work was based on the Standard Imaging LUCY MR Phantom, which is their anthropomorphic head phantom that is both MR and CT visible. So now I'll talk a little bit about the design and development of the insert. So the insert was created using 3D printing. For those who may not be familiar with 3D printing, 3D printing is a type of additive manufacturing. There are many types of additive manufacturing methods, which vary a bit in complexity as well as cost. One common method is called fused deposition, FDM, which for any nerds or DIYers out there, they might be familiar with. It's essentially extrusion of hot plastic, usually PLA, layer upon layer to build a 3D object. You can see Mr. Groot being made 3D printed on the right. In this study, material jetting was used to build the insert. So this method uses droplets of photopolymer material, which are jetted onto the build platform, then cured by a light source layered by layer. So the benefit of using this type of method for 3D printing is that you can actually kind of dope the material and mix a different type of material, mix different material mixtures. So for this insert that we created, we use a material mixture of tissue matrix, Vero, and radial matrix. And so we worked with Ryko and they created a 3D test object, which we were able to MR as well as CT. So the image, this image shows the little test object, and this is a screenshot of the MR, which is shown in blue, and the green, which is shown, CT, which is shown in green, where we try to evaluate tissue equivalence using the HU units of the CT, as well as MR visibility. So after we figured out the optimization of the material, we created the insert. The insert design was actually based on a patient that we treated at our institute on our MR-Linac, in which we eventually adapted offline. This is a screenshot of the patient on the planning, we call it a trophy image, where the orange is the original volume and the magenta is the adapted volume, where you can see that the volume actually shrunk. The DICOM structures were exported and post-processed. You can see they were smoothed out and then aligned inside the inserts for areas with an ion chamber as well as a film. And the final result is shown on the very bottom left with the target actually placed inside the LUCY MR Phantom. Now talking a little bit about the Phantom imaging and adaptive delivery. So we had the ability to image the Phantom on 4 different MR systems and 1 CT system. So it was imaged on a Philips Big Bore CT simulator, and the 4 different MR systems include, of course, the Viewray, which is 0.35 Tesla, the Unity, which is 1.5 Tesla. We had ability to scan it on a 3T MR sim, as well as the Magnetom Free Max, which is 0.55 Tesla. This just shows the different images from all the different modalities. You can see that it shows up nicely on all the different imaging modalities. One thing that we noted was that it was not visible on a T2 image. So you can actually see this is the trophy, which is a blend of T1, T2, and you can see it shows up nicely on that planning image. So for the planning, we actually created a pre-plan or a base plan on the small target, and then for the adaptive fraction, we switched it out with the larger target. So the goal for the planning was to prescribe 9 gray in 3 fractions for a total of 27 gray. And the main objective was to achieve a normal brain dose of 30 cc less than 18 gray, which is a typical radiosurgical constraint used from Manetti. So this is kind of our results showing the ability to get fairly good conformality and gradient indexes for the MRidian as well as the Unity, as well as that normal brain volume below 30 cc in all the different scenarios. And finally, just showing some gamma analysis for the film from the insert. For 3%, 3 millimeters, for the pass rate was 99.5%, 98.6% for the Unity and MRidian. And then for a tighter constraint of 3%, 1 millimeter, 88.1% for the Unity and 90.35% for the MRidian. So in conclusion, we were able to develop a MRCT visible insert that we use for intracranial adaptive RT. We successfully performed online adaptive workflows on both the high and the low field MR-Linacs. And one of the really exciting things about this is that we can really use this phantom to validate and further improve our intracranial FSRT adaptive workflows. Finally, I'd just like to say thank you and acknowledge the whole entire team. You can see this is very collaboratively, the Henry Ford team, the Corewell team, who owned Unity, and a lot of the other imaging aspects that we worked on, and as well as RICO and Standard Imaging. Also, I'd like to note that this work has been submitted as a manuscript. Is under peer review currently, so if you're interested in more of this work, we hope to have it published soon. Thank you.
All right, so thank you, Karen, again for the wonderful presentation. So now I'll follow up on another phantom that we have, which is the LUCY ThorX. It's a pseudo anthropomorphic phantom for SBRT and imaging QA. So you can do end-to-end imaging, mechanical, and dosimetry QA for the CT simulator and the LINAC. So it can be used to test kind of key components for APM TG53 for TPS QA, 66 for the CT sim QA, and also components for the TG142 and MPPG8A for the LINAC QA. And of course, you can use it for SBRT end-to-end commissioning. As you can see, there's sections in this phantom. So in kind of the superior sections where you would do more of the imaging tests, and then on the inferior end, you'll have more of the features for SBRT QA. So within the phantom, these are the targets for kind of your SBRT QA, where we have the targets and the margins. You can see there's the kidney target and then kidney margin, and the triangle target and margin, and also there's a target within the film rod insert. We also supply, so these are where you can put kind of the ion chambers, and in the ion chamber solid plug, we also supply an embedded BB. So this can be used to plan where your target should be for and this matches the active volume for the ion chamber. And this nice thing about the multiple ion chamber cavities, you can do kind of a multiple MET, right, with a single phantom. Of course, for treatment deliveries with sharp dose fall-offs in SBRT, film is the best tool to be utilized for this. So for this purpose, 2 insert films are included with the ThorX Phantom. The film rod insert on the left has the film bisecting the target, and the insert can also be rotated to capture kind of dose distribution off of the cardinal plane if needed. And then for the spine insert, there's also a film bisecting the 3 pseudo vertebrae and spinal cord. And the custom cut films, they all fit into the dowel pins. You can see the black pins there for precise location and quick and easy alignment for analysis of the film. So going into kind of adaptive, so these are the set of inserts that we have here that we're developing. Is the adaptive insert in a prostate case, right? The classic case of a kind of a full bladder and an empty bladder. There is a film plane, as you can see here. It's actually small film pockets. It might be hard to see in the screen, but and then also similarly, there's just going to be dowel pins there where you can locate the film. And also this ion chamber cavity as well, going right into the prostate. And there's also another option, which is for the spine case, where you have a straight spine and a curved spine. Similarly, there's a target there, and then ion chamber cavity right into the target. Just showing you some images here that Karen took. Is from the Halcyon machine or Ethos. Here on the left is the full bladder case, and then on the right is the empty bladder. So just kind of showing the segmentation and contouring of the prostate, urethra, bladder, and bowel. But depending on your system, some structures can be auto-contoured, but you may have to do some manual contouring for some of these structures too. Just showing here the thorax in the bore, and there's some film analysis here. As you can see, the plan and film dose agree, quite well, 3%, 3 millimeters. And I think that brings us to the end of the webinar today. Obviously, if you have any questions, please put them in the Q&A. We can try to address them right now. So let's see if we have any questions.